So let's make a start. So some of you will have been to our meetings before. We're Bedfordshire Climate Change Forum. Tonight's subject, as you know, is the Archimedes screw on the Great Ouse in Bedford, which is coming up for 11 years of micro hydro generation. So its birthday is actually, I think, next week or the week after. And of course, I'd like to introduce Will Rawes. So Will, as you may have seen, is a local physicist, formerly of Cranfield. He has a PhD in fluid engineering, amongst many other qualifications. He's a really strong advocate for local renewable energy, not least the potential for hydropower locally and nationally. And he's going to talk, as I said, for about 40 minutes, and we welcome your questions and comments right after that. So, thank you. So I'll hand over to Will.
Hello. So as Lucy said, my name is Will Rawes, and I studied fluid engineering at Cranfield some 20 plus years ago, and have since also worked at the Open University for about 18 years doing software for teaching physics. And so physics is really my passion on the academic side of things. And I was very, very excited when the Archimedes screws got built. And in fact, I had the pleasure of being able to commute on my bicycle past them twice a day for many, many years. And in one sense, that's helped result in today's presentation. So I will share my screen and just go to here and put up the slides. And hopefully everyone can see the slides. So the River Great Ouse, a wonderful river which makes Bedford, has got these Archimedes screws built on them in the middle of Bedford, and I've been logging them particularly obsessively in the first 3 years of their activity. So from 2012 to about 2015, I cycled past them and took a log twice a day on my commute, and sometimes at weekends, and sometimes I'd ask friends and family to join in and just ask if they could log what they saw of the screws doing when they went past. And this was all done at random times of the day. However, when you get a lot of data, then in fact you can start to use it and things become quite interesting, and you start to see actually how effective these things are. So here we go. The Archimedes screw, I would recommend going to the Wikipedia articles on all these various topics that I talk about. The Archimedes screw was invented maybe 200-ish plus BC. And so we're looking at 2,500-year-old invention. And we have these rather strange sort of responses to such an incredibly simple and I would say elegant device. And in fact, originally it was invented to go the other way around. It was used for pumping. It was invented by Archimedes as a way of lifting water. And in fact, in no circumstance really would you ever have wanted to use an Archimedes screw the other way around until electricity came along, because you wouldn't need to be really driving many things. Perhaps a water mill, yes, but it's interesting that really it was invented to go the other way around, and yet when it's going in this direction, it works completely reciprocally. And that means the same mechanism forwards in time as backwards in time, and things like the efficiency and things like that are not impacted by the direction in which it's going. So this is actually a very, very elegant machine, which a machine converts energy from one form into another. And in this case, it's changing or redirecting movement energy. And the original source of energy typically is going to come from gravitational energy, where an object or a fluid falls from a higher point in space to a lower point in space. And that always, 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 always releases energy. And it's absolutely fundamental to the universe. Now, what's interesting is that we have headlines like this. And in fact, if you Google the Archimedes screws, you often actually see headlines that reflect somewhat the negative, as in these have been built in the wrong place. Now, I do wonder, I was intrigued as to really how much energy these things produce. And so this is what we're going to have a look at in these slides. And we're going to see if it's worthwhile or not. So 20-ish, 12-ish, they were opened by the council, and they, in one sense, did stick their neck out and take a risk financially to consider investing in this with a capital expense of, I think, about £500,000, which obviously, when £500,000 suddenly gets spent with other services that are required, then that can cause perhaps concern. So there was some concern. Now, over this period of time, in the first 3 years, I've made this little report, which actually I think if you contact Lucy or BCCF, then we can make links available. And in fact, I think we will even try and work with the council perhaps to improve a page on their site to update some of the technical and factual information about the screws. And so I've made these 5 odd pages which describe the approximate estimates that I did visually as a physicist, obsessive physicist, you could say, and I've made observations and estimates of roughly how much power, from a physical point of view, these things would generate. And so I came up with some figures, and I was wondering if maybe they were producing something called maybe 17 or 18 kilowatts of power. And we're going to look a little bit later about what actually is a watt, because I've only had a recent experience of learning more deeply what a watt is, and it's quite fun. Then over 3 years, I collected lots and lots of data and plotted this crazy, messy looking graph, which actually the real world is full of mess and full of complicated things, and nothing really is much of a straight line. And in fact, we've got a nice little video. So if I play this, then here we go. I hope you can all see that. What a wonderful thing. So this video is what I used to accurately look at the speed that the screws were turning. I hope everyone can hear the water. So, sorry, I need to come out of full screen. There we go. That video I used to accurately measure the speed at which the screws were turning, and then that meant I could make a reasonable, potentially, estimate of how much water was flowing down per second. And when you get a flow rate of litres per minute or something, or litres per second, and then when you combine it with how far the water is falling a vertical distance, then that equates to an energy. It equates, you can actually calculate a power. So we have this beautiful setup. And another thing about this £500,000 that was spent, I suspect, and I don't actually know, how much of the cost was actually spent on making it look beautiful, because personally, I do think it looks beautiful. I met with council some days ago, which was wonderful, and they gave us some extra information about the build, and they said that it was designed architecturally to fit with the neighbouring boathouse. And in one sense, nothing is isolated, everything generally is connected. And so the boathouse for recreational rowing, which is very extensively done in Bedford, there's 4 or 5, maybe 6 rowing clubs. And so the river shares services for many, many things, which is recreational, there's barges, there's boats, there's the wildlife, there's a lot of swans, so there's lots of very important aspects of the river that are not just the ability to produce energy. And you can, if you Google the screws and get to the bedfordgov.uk website, then there's an environmental summary page, and you can keep up to date with some of their latest published figures. So that you can keep up to date with that on that site. And I personally think that actually they've done a very, very good job. Now, this is photos of the build from 2011, 2012, and Spahn Babcock was the company that did the build. They've built Archimedes screw systems around the country. I would say not enough, because I do think that the potential with weirs around the country is so enormous that I think more significant contribution could be made to the energy mix of input for UK power. And we all know, even more so the last few years, how critically important that is, that micro local power generation can be very effective. It can have a certain independence, a certain robustness to it if the devices are maintained and robust. And a very, very significant thing about an Archimedes screw, let's have a look at it. I don't know if you can see my mouse, but the main component is this one massive bit of metal. Now, you could say there's not much going to go wrong with that. It's an incredibly simple piece of engineering, and you should never, never, never look down on things that are simple. Never. Often there's a trendiness that will look down on stuff like this, but that's ridiculous, because this device is so inherently robust. The only thing that counts is the quality of the bearings, the longevity of the bearings, and the reliability of the electrics that's being used to generate electrical power. And as we know, it's a 2,500-year-old invention. So these sort of things are really, really worth considering. Now, I'm just going to quickly demo, or we're going to ask the question, actually, what is a watt? So these things, which are reliable and beautiful and noisy and generate power, they produce this stuff called kilowatts. And I just wonder, does anyone actually know what a kilowatt is? I don't know. If you know what a kilowatt is, then maybe chuck it on the chat, and we could talk about it later. And what actually is a watt? Now, watt actually comes from James Watt, who's pictured here, and he was working on basically the expansion of the understanding of physics, energy, time, space, movement, weight, along with people like James Joule, using Newton's laws, and they were discovering some of the very simple but rather, shall we say, we could say secret. I noticed that the newspaper headline said revealing the secrets of the screws. We could say that understanding energy mathematically or in a quantitative way isn't entirely obvious. So we could ask, what is a watt? And the thing we're all paying for, and is in the newspapers every day and on the TV, is how much you're paying for your energy. And you pay for your energy, whether it's gas or electric or oil. Actually, well, oil's in the physical mass, but at the end of the day, these energy providing things, stuff, give you kilowatt hours, and that is the basic standard unit of price for energy in the UK and actually a huge amount part of the world. The kilowatt hour actually is the unit of energy, not power, where if you were having a kettle switched on that was running at 1 kilowatt, if you had it on for 1 whole hour, it would use up 1 kilowatt hour of energy, and you would then pay for that at a price, and this is the price that goes on the stock markets everywhere, and everyone worries about the price, and it's going up and down, and of course it causes lots of concern, and it can have big impacts on society. So the price of a kilowatt hour is really what counts. But again, what is a watt? Let's have a little look at this. Now, here is a video of my kettle, which I did this afternoon, and let's just play it and see what we find out.
So I've got my electric kettle here, rated, says 2,500 to 3,000 watts, so that's a 2.5 kilowatt kettle, which is pretty powerful. And as you can tell, it's empty. It's just been upside down. And I've got 1/4 litre of water here. So I'm just going to pop it in the kettle. And we're just going to see a picture of what our daily sort of energy consumption can easily be. Being like English and making cups of tea, with the question really of what is a watt. So I'm going to switch the kettle on, but the exciting bit is that we're going to be looking at the meter up here. This is our house electric meter, not much else is running. One little clip there shows that an impulse has gone through and there's 1,000 impulses per kilowatt hour. So that was 0.001 kilowatt hours of power just gone through in, what time was that? I don't know, maybe 5 seconds. But when we put the kettle on, which is running at maybe 2.5 to 3 kilowatts, we're going to see those flashes increase. And there's maybe a computer running, maybe we're running 50 or 100 or 200 watts at the moment, don't know. We can do a timing with the clock. But let's switch the kettle on, which is a very normal activity, and see how many kilowatt hours we sort of wang through while we try and boil 1/4 pint of water. So I switch on it goes, and let's just look at the plips. So that's the rate of plips going through now. So if we count, say 15 seconds, when it gets to 3, we'll count how many plips you get. And with the second hand going through, I'm going to count in a minute. I'll do 10 seconds. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we've got a plip of about 1 plip a second, and we can do some sums in a minute. And here's our kettle that's boiling 1/4 litre of water, and that is the sort of time it took. So now we can do some sums and see what energy rates we throw around our houses.
Right, so that is a video of a physicist having fun. If you're a physicist, it's utterly compulsive. Yes, this is what physicists do. It's genetic, I don't know. Now, let's just have a little think. This happens all the time. All the time. Every house is doing that sort of thing. And that's only to have a cup of tea. So what the video showed, once I've clarified my units a bit, I'm going to call them blips. There were 13 blips in 15 seconds. So we know from the instructions on the meter that that was 0.001 kilowatt hours per blip, and we had 13 blips, so we used up 0.013 kilowatt hours of energy in that 15 seconds. And then the overall boiling process of that 0.25 litres, I'm thinking it's probably about 80 degrees centigrade change in temperature from 20 to 100 to boil. And so I put that into a little physics sum here, which uses one of my favorite numbers, 4.2 joules per gram per degree C, which is a beautiful, incredible property of water, which again, water's incredible. That's why we've got Archimedes screws, but it's also why it's good for storing energy. And we used, I'm thinking, around 84,000 joules of energy, which is in the kilowatt hour unit, 0.023 kilowatt hours. So that's not too much, and we can afford to probably boil a cup of tea. The overall timing was actually just under a minute, more like 40 seconds. And when we do how much energy we used over how much time, then in fact, joules per second is a watt. And that is what a watt is. And we used the rating at which we were heating that water turns out to be pretty much within the spec of that lovely kettle. We used 84,000 joules, which is actually quite a lot by the sounds of it, and it actually is. and the rate at which the kettle ran was 2 kilowatts. Note, 2 kilowatts of power use is actually very high. It tends to be one of the highest things you will be using in your house. Washing machine, maybe a kilowatt, maybe less. Electric drills, depending on the power, maybe a kilowatt, maybe less. The kettle and your water heating and your immersion heater, if you ever use it, is the thing that will really be eating up your electrical power. And then that puts the drain on the grid. And the UK grid is fascinating. You can go to a website called UK Grid Watch, or there's a Templar one. There's some very good live UK grid pages. And they have, I think, something called, I can't remember if it's Coronation Street Hour or something, but at various times, particularly in the past, where there were old TVs, that when certain TV programs finished or started, there'd be a huge pulse in the generation of, cups of tea, or kettles were put on, and there was a very high surge in demand in the national grid, and the grid see all these spikes, and it comes from this. So this page really shows us what the grid is actually having to provide us with, and it's incredible, isn't it? I can switch a switch with virtually no effort, and suddenly I can be wanging 2,100 watts of power through a wire. And it's interesting how much we take for granted, I suppose, what goes on in life around us, because it happens without us seeing. So let's go to the watts, although wattage is not a proper word. We could look at what I collected from the Archimedes screw. So in the first 3 years, I collected maybe 2 times 360, maybe 700 points a year for 3 years. So that's 2,000 data points. And I put them all in this spreadsheet down here. So there's lots of lines there. And I gave a sort of rating based on the video of the speed of the screws and the calculations of how much water was flowing. I gave an estimate of what sort of power of water would be flowing. And I collected it and plotted it on this graph, which I love doing. Physicists love graphs, and so you can't beat a nice graph. And this graph can tell us many, many, many things. Very interestingly, I was very sad when a cable was cut at this point and there was no production for a month or so. And so the average of power output went down and there's a big gap, and I was very sad, but then it came up again. And underneath, I also plotted rainfall of Oxford and Cambridge Met Office stations, and we can see there is a correlation between rainfall and output of screws, and that's very important. Also, on this side, I hope everyone can see the screen just now. I've got my thing in the way. So I looked at the sort of average type output over each year, and the average is sort of drawn by the red line here. It's called a moving average, and this sort of line is critical to any proper science. And when you read newspapers, often you do not get proper science, because you might get a science article that talks about a little blip down here, or a science article or a media article that might talk about a blip up there. And often the average, which is the critical, rather boring figure, is actually the most important. And so over the last few years, it looks as though the screws are working at perhaps 400 or 300. I've got my screen in the way. Yeah, so we're perhaps getting 300 watts out of a 700 watt hours per day unit capacity. That was based on my observed estimates. And then what happened was we had some published figures of the output from council as they were looking at the kilowatt hours that were transmitted in real through the wires. And it turns out that the estimates that came from some physics are actually not too far off those from the actual figures. Now, in fact, I've learned recently that I think I had, by my estimates, overestimated the energy output of the screws, because the published figures are based on the real figure, which is slightly less than my physics one. But it was very exciting to see that actually they do correlate, and they're not too far out. I mean, 154 of the real against 160 of observed. So that I don't know, I was very, very, very excited about that. I did tell my friends about it quite a lot, and family, and yeah, anyway, it's better to do a talk like this. So that was really good fun. And then we can then sort of look at an approximate efficiency measurement, where using the figures that I'd produced from my observations, it looks as though in 1 year, what have we got, 2014 to 2016, 400 kilowatt hours were produced. And so that would mean, compared to the published figure, in fact, so what am I doing there? I think I've actually got a bit of a mistake in here, but yeah, that's it. I'm saying more's produced than was thingied. So I'm out by 90. I've got an error overestimate in my power. But the important thing is that the efficiency, which is used in these calculations, so this 36.5 kilowatt number here, actually is assuming a certain efficiency of the screws, where we can know how much water is flowing down at a flow rate from a vertical fall, and we can put an efficiency figure into this number here and compare what you actually get. And these calculations show that this device, even just a simple Archimedes screw, moving rather slowly, just over quite a low head, is still in the region of 90% efficient. So just to clarify, these red figures here are based on my estimates, and the real ones are reduced. They're slightly different, but the overall efficiency of water falling through something like an Archimedes screw, or even a normal turbine blade, is incredibly efficient. And we could think, well, why is it so efficient, and why don't we use it more? That's often what I do think. One of the reasons water hydro energy is so efficient is because, again, of the properties of water. So water itself is actually very, very heavy. 1 meter cubed of water weighs a ton. And another factor that makes water an efficient energy transferring medium is that it's also got a very low viscosity. And we all know that, because when we get leaks in pipes and things, boy, does water get around. So its high density and its low viscosity and its high availability really make for hydro power generation, just on physics principle alone, to be well worth doing. The fundamental principle of hydroelectricity being so efficient actually means it is worth pursuing. And I've always been had a close eye actually on the project called the Swansea Tidal Lagoon. And the Swansea Tidal Lagoon project was started a long time ago, and a huge amount of investigation and investigative research has been done, even to the point of perhaps building prototype devices like this beautiful photo, which is one of my favorite photos actually. It's a turbine blade that could be one of 16 that goes in the lagoon dam wall of Swansea Tidal Lagoon. And although it's a completely different shape from an Archimedes screw, actually in terms of its energy efficiency and transfer of energy from moving water into a turbine, then in fact it's still got that incredibly high efficiency, again because of the properties of water. And so fundamentally it's a beautifully efficient thing to be doing. Now I've had some fun recently, because I've been doing a course at the Roths Education Centre about energy generation. So we got this big picture of a turbine, and I've been we're thinking of how we can demonstrate how this blade here, pictured here, can generate electrical power. So this is a slight little bit of fresh air aside, and I've got a friend with me here who I've called Colin, and he's an oscilloscope. Oh, no, sorry, not Colin. That's my carbon monitor. This is Oscar. This is Oscar, the oscilloscope. I've been lent it by a good friend, and Oscar is set up to observe any electrical current or voltage, let's say voltage, that's generated across these little wires here. So rather than just listening to me talk, here's my fishing reel, which I've had for 30 plus years, and I loved fishing. Again, water. I must have something about water. I don't know. Anyway, and I took a little bit of red wire and wrapped it in a coil a few times, and then I put some magnets with sellotape around my fishing reel, so that when I spin my fishing reel, the magnets whiz past the coiled wire. So let's imagine that this fishing reel here is connected to these huge turbine blades that are in the wall of the Swansea Tidal Lagoon, or actually another wonderful place is the Renewable Reservoir. There's loads of wonderful hydro places. And then my friend Oscar might show us something when I start moving the magnets past the wire. So if I do it slowly, then in fact you don't see much. But if I get my wires out of the way and then start spinning the wheel, I think we should see some activity. So here we go. I don't know if you can see that. I can. It's such fun. But when I spin the magnets past the wire as spinning from a turbine, then in fact we generate this beautiful, beautiful electrical current that comes from fundamental laws of nature. Actually, they were actually properly mathematically described by a guy called James Clerk Maxwell, who's one of my favourite physicists. Oh, hello. How's screen sharing going? Oh,
I just stopped sharing screen, Will, so that people can see you better.
Right. Sorry, did something go?
No, that's fine. It's fine.
Oh, okay, fine. So anyway, that's what happens really with all these turbine blades. Wherever you see them, although we don't see the blades, although happily you can see the Archimedes screw, but all these hydro generation schemes are fundamentally doing that. They're turning efficiently with the water pushing the device, and that's how it works. Lucy, do I need to share a screen again to get back to the slides?
Yes.
Right. Let's just do that. And I just want to, this bit here, I would like us just to consider that in 2017-18, Charles Hendry of the Conservative Party, I think business minister of some sort at that time, did a very, very extensive review of the Swansea Tidal Lagoon proposal. And he one of the critical conclusions was it was important and clear that tidal energy in the British Isles at scale could actually deliver a low carbon power in a way that would be very competitive with other energy sources in the UK. And although, I mean, there's lots of competition all the time with the best and the most and the cheapest way of generating power all the time, there's all of that all the time, solar, wind and nuclear, all these things, depending what one's view of nuclear is. But what is definitely true and will not go away is that the Bristol Channel is in the top 5 of highest tides in the world. And that is such an incredibly stable source of energy. And it can be tapped using inherently efficient, 90% efficient hydro technology with very, very simple, low-tech technology. And in fact, I've heard from our meeting with Bedford the other day that their maintenance costs for these Archimedes screws is very low. I think I just have to oil the bearings mainly and then check the electrics and deal with the floody sort of stuff, apart from it's contingencies built into the system there. So the maintenance of hydro is low. I mean, just imagine what the maintenance cost of hydro must be compared to maintaining the safety of a nuclear power station. I mean, you know, the actual costs are it's going to be nothing, isn't it, compared to keeping a nuclear power station safe. And so were all of those costs taken into account when the government at the time didn't actually support the actual development of these screws that actually the Hendry review actually recommended? I don't know. So I'm going to guess I doubt it. And also this was also done before the time of the more recent crisis, energy crisis, that's been facing Europe and the world of the last few years anyway. So yeah, I don't know. I think that's a sort of quite a lot there. Maybe people have got questions or concerns. That's more or less it. We can go back to other stuff if you like. I have got some web pages which may be of interest, such as the De Norwich Power Reservoir, which is a hydro system of the last 30 years that's been brilliant. Don't know. We can talk about it if people want to think about that.
Thank you, Will. Thank you for your enthusiasm, and we like the demonstration of what's really useful.
It's all fun.
The physicist in you. Has anyone got any questions or comments? I know we've got some people who are.
I'll just turn Oscar down so that he doesn't flash us out. There we go. Good.
Thanks,
good
Will.
Oscar.
We've got a question from Anne. Anne, do you want to unmute yourself and just ask?
Yep. I'll give you some video as well, if I do exist. Yes, the quote about being in the wrong place might even have come from me, because I did put in a comment when they were doing the planning permission for the hydro to that effect. And what you haven't got is the context on it. Now, if you know Bedford well, you will know that at the point where they put in the Archimedes screw, there are 3 separate streams to the river. So there's the top river, what goes over Duckmill, and there's the bit that goes round by Boat Slide, only part of which, because there's still a weir there, is used by the Archimedes screw. So we've got less than a third of the volume of the water that goes through Bedford going down that. I've just been looking in the IMRE guide about it's actually the Bedford Lock, and I think the bit that is relevant is the depth is about 1.1 meters. So
are we talking about the head drop sort of thing? Yeah. Yes, the head drop.
So it's not
critical. That's the critical factor.
Yeah, that's right. It's not all that great again at Boat Slide, which is where the Archimedes screws are. Yeah, when you compare, if you know Castle Mills, and that takes the entire volume of water for the whole river, all over Castle Mills Lock, and according to that, they've got a fall of 2.7 meters on that.
Right. Yes.
So I mean, it's massive by comparison.
Yes. Yeah.
So I mean, my argument was, I mean, it's a brilliant thing to want to use the river for hydroelectric, but surely they should have used Castle Mills.
Well, no, look, I'm going to say no, because it's obvious to do it at both, isn't it? I mean, to be honest, why should there only be one Archimedes screw within a 50-mile radius of here? That's insane. To me, that's the insane thing. Not that it's built there. You know, the fact is, we're one, you know, we've got this talk now about an Archimedes screw, which is 2,500 years old. That's, to me, is the ridiculous thing. And there should be, you know, if we were mass producing, you know, if we had a decent Archimedes screw industry, then in fact, it wouldn't be costing £500,000. We would, and so that's the problem. Now, in terms of the question about the head, yes, there are the various weir points for the 1.1 meter head, but I do understand that actually having it totally visible within the public place, within the middle of Bedford, I think is a good thing. And that's actually, again, why this talk's been able to happen, because we've all got this sort of, my goodness, what is going on with these things? Are they any good? And the answer is yes. And in fact, I think these things are exemplary. absolutely exemplary. And I actually learnt myself doing that obsessive observation project that the stuff is 90% efficient. It's ridiculous. I mean, it's so I think it was a very, very good thing. The fact that it cost £500,000 or whatever it cost, which, you know, was thought to be too much, I'm thinking, well, actually, they've made it incredibly beautiful. You know, it really is beautiful. And the thing is, now we know it's brilliant. Well, darn well go and build an Archimedes screw at that 2.1 metre drop place. But also, very importantly, is we cannot get all the energy out of everything we want. You can't do 100%. So the Environment Agency has to play a very significant role in maintaining the integrity of the River Ouse, flood-wise and drought-wise. And so there's a huge balancing act that has to be played between the services of a river required. So, but yeah, my view is these wonderful, very small micro screws have actually demonstrated themselves impeccably. I think it's just such a good example. It's actually demonstrative of, for goodness sake, there needs to be an industry in this. I mean, you know, the weirs of Bedford they're okay, but I mean, there's other more significant weirs around that could be contributing to a stable energy mix for UK energy. And the stability is very stable. And yes, it's dependent on rainfall. So that is a significant factor. But, you know, to me, it's a brilliant exemplary example of demo of, you know, we need to do it. It's just obvious. This is low tech. And yet it's very significant tech. And we shouldn't just, you know, yeah. But yeah, in terms of saying wrong place, and sadly media always picks up on the extremes, like, you know, with the graph that I showed, you'd go headline about the lowest point or headline about the highest point. What's the average? The average is good, and it demonstrates it's worth doing more. That's my view.
Yes, I mean, I very much agree with your points there, which would be really valid. I mean, in the years that we've had the Archimedes screws in, we haven't, as you say, we haven't built anything. There's nothing closer than, as far as I know, Oxford. I think
yes,
there's Oxford, isn't there?
I think London. Well, there's probably a
Windsor.
Yeah, but anyway, look, there's not enough, is there?
No, not enough.
Obvious.
Yeah, need to be doing lots more. Yeah. Thank you.
Yeah.
Thanks, Sam. So I think we're all in agreement. Hopefully we're all in agreement. We need more. Their potential is huge. So, question from John. John, do you want to?
Yes, thanks, Lucy.
Comment?
Yeah, well, great talk. Thanks very much indeed. Yeah, I mean, one other thing, of course, is that it's happening 24 hours a day, isn't it?
That's right. Yeah.
People who are against it say, oh, the sun isn't shining all the time, or the wind isn't going all the time. Well, this is, unless there's a big drought.
Yeah. Interesting just to note that when we were talking with council about how to perhaps improve it, it could be that the weir potentially could be adjusted next to it to try and divert more flow through the screws. There may be some actual real advantages to that, even from the wildlife point of view. We'd heard that cygnets can actually get a bit stuck in the wide weirs, but I think there's always ways of doing some innovative tweaks and adjustments to improve it. So I think that could happen. But yes, stability is the big one, I think.
I was looking at one of your graphs, and I think it looked like rough average 280 kilowatt hours per day on one of them.
So
if that is the truth,
I'm not gonna change my machine at this point. But what I remember, just a minute, is it? I think over 24 hours, I estimated it's 30 kilowatts ish when they're running at full. So if they're running at full, both of them at 100% for 24 hours, I think I got to 700 kilowatt hours per day. That's if it's 100% efficient and running 100% of the time. And I think the running time's more like 35 or 40% of that time. And I'm very happy if you want to make contact via Lucy or something, then we, you know, if you want to play spreadsheets, then we can.
No, I was
you can have it if you like.
So you confused me now. Is it 28 kilowatt hours per day or 700 kilowatt hours per day?
I think it was 700 kilowatt hours a day. So if both screws are running at full, And if they're producing 30 kilowatts,
Yeah.
then over 24 hours, that is 30 times 24 kilowatt hours.
Right. Okay. So,
You simply multiply a kilowatt by the number of hours that you're burning, as it were, that kilowatt. That it's a funny thing when kilowatts and kilowatt hours are thrown about, and it's easy to be out by a factor of 1,000 when you're talking about it. I do. So, yes.
Yeah. Okay. So if it's 30 kilowatts, a typical solar panel is about 300 watts. So you're talking about the equivalent there of 100 solar panels. So
That's right.
this goes to show, doesn't it? And that, of course, is only about 8 hours worth of power out of a solar panel.
That's right. Yeah.
So you're talking about the equivalent of 300 solar panels.
Yes, that's right. Yeah. And I would never. I think energy mix is very important, and energy mix is very important. Stable energy mix, I think, is the thing to always go for. So, I'm not against solar panels, but the mix is important. And I think sometimes if we monoculture onto anything, if we go onto a mono magic bullet solution with one thing, then actually we always tend to mess it. That always has problems. Yeah,
we've got 12 solar panels and a couple of batteries on our house. So I'm not against solar panels. I was just using it as a demonstration of compares with solar panels.
Yeah.
Great. Thank you very much, Will.
Yeah.
Thanks, John, for that. We've got a question from Richard who in the chat, because he had a problem with his audio. We're normally talking about carbon and energy resilience, but he's got a good question about the financial aspect. So he says 294,000 worth of electricity since 2012. Obviously, we don't know what the price was then, but the market tracker he mentions. So that would mean the payback is 16 years. He said, I think that's excellent. So the financial case is as beautiful as the physics case. Do you agree?
Well, yes, I have actually asked others whether or not that's good. And actually, I've heard that that's actually I think it's a very stable capital investment type sort of cost, really. And potentially, depending what happens with electricity prices, it might even improve. We don't know. But yeah, if it's stable and reliable, then financially as well, that's all good news, isn't it?
Absolutely. Yes. So Colin, you've got a question?
Yes, thank you, Lucy. Yeah, really super talk, Will, and very inspiring. As you know, I'm not a physicist. I just wondered if you could give us some idea of the sort of scale of power that the Archimedes screw in Bedford generates. How many households? This is the...
Oh, yes. So, I can
just extend my question. Just extend it. So it was, how much does this Archimedes screw actually generate in terms of powering households potentially? And then I wanted you to kind of dream, supposing all of the sort of opportunities that you've spoken about, the Swansea Tidal and all the other opportunities were utilised, what fraction of our energy usage could hydroelectrics meet in the UK? So it's all about the kind of scale of it.
Yes, the scale. Yes, it's nice to have nice ideas, isn't it, and to do funny things in a shed. But so yes, the Archimedes screws, if they're running at 100% and 100% of the day at 30 kilowatts. In fact, if you look at, I think the typical domestic citizen household consumption averages to be about half a kilowatt over a whole day. So with our kettles and our TVs going on and off over 24 hours, it's the same as perhaps burning off, as it were, half a kilowatt all the time. So if the Archimedes screws are running at 100%, then 30 kilowatts of the screws turning all the time is enough to power 30 divided by 0.5, which is 60 or 70 households. So if they're running, that's what they can produce at 100%. 60 or 70 households can be powered consistently from that device. And so that, yeah, I think that's a good thing. And obviously based on thinking, are they in the wrong place? Well, no, yes. If there were ones at the 2 meter drop place, then you would get potentially twice, maybe 3 times the power out of that one. So let's just build that one as well, I'd say. Now, when you talk about the Swansea Tidal Lagoon thing, I don't know, shall I share a screen and go to the Swansea Tidal Lagoon page, or shall I do that?
Yeah, go
Okay,
ahead.
let's just share. We'll go to the Tidal Lagoon site, which I am a bit of an avid fan of. Where did I put it? He says, hopefully not wasting time. No, oh gosh, just a minute. Oh, here we go. Right. So here we go. Here's the, can you see the Swansea Tidal Lagoon page there? The amount of work that's gone into this proposal, I think, is incredible. And to be honest, I even think that it looks like a beautiful thing. It's a lagoon. So it's not the same as the Severn tidal barrage, which was a nightmare consideration, really, 40 years ago, to build a whole dam across the whole of the Severn and really significantly disrupt bird life and mudflats and all of that. But a tidal lagoon is different because you are only knocking off a section like a harbour. I mean, we've got harbours all around the country anyway. And actually, I understand that British marine civil engineering is brilliant. So we could do it. And I wonder, if I was a mollusk, I think I might quite like living on that lagoon. I think it could be incredible. So the plan is, I hope it is done, to have a lagoon structure like that. And maybe, to be honest, maybe you could just do a straight wall across there instead. I don't know. But this has been the plan that the Henry Review went into great detail about, with that lovely report. And actually on this website, if you Google Swansea Tidal Lagoon, there are some pictures of the design where there'd be 16 of those blades in the wall, and they would be turning in a balanced way with the in and out of the tide, which is twice a day, in, out, shake it all about. Twice a day that occurs, and those blades would be spinning probably most of the time. Incredibly stable power. And I don't see, in one sense, I mean, it may sound a bit much, but suppose there was 100 of those around the 10 metre or 8 metre tidal area of the UK. And if it was done sensitively, and if it was done well, I might guess maybe could half the power for the UK come from stable tidal power. The Bristol Channel is incredible. Just go to Google Maps. Just look at the Bristol Channel. It is a funnel that's getting 10 metre tides because the whole of the Atlantic Ocean is leaning in and out and in and out of that funnel twice a day. It's incredible. And it's such an incredible natural resource. And it can be utilised. And overall, in terms of costs, the reason I think it was rejected was probably because some people said it was too expensive, because maybe I suspect not all considerations were taken into account. I mean, to be honest, they wouldn't have been, would they, with the surprise of the last 3 years? And so I think it would have been completely viable. And the maintenance cost and the longevity and the simplicity of a tidal lagoon, I tell you what, it's just through the roof in terms of simplicity. And it's beautiful. I mean, I think we can do it. There's no reason not to do it, really. I don't think. So yeah, I think, Colin, in terms of dream answer, I'd say half of UK power. I don't see why not. If it's done well, and if everyone becomes a stakeholder and is on board, if everyone if it's mutually beneficial, then that's great, isn't it?
Can I just say, wow.
Yes, I mean, look, would you like to be a mussel or a mollusk on those rocks there? I would.
Absolutely.
Yeah. So, yeah.
Thanks, Will. That's incredible. The idea of generating half our energy using
I think
Tidal is staggering.
it's possible. I'm just going to do Control Tab. I mean, look, just stats on the big game. Norway is 98% hydro. When it rains, price of electricity goes down. Right? They've had that for 80 years plus. I've seen pipes on the hills of Norway, 3 kilometres long. The pipes are made out of oak barrel. They're that old. Now, obviously, they leak a bit now. But, you know, for goodness sake, this is not rocket science, and it can be done. And, you know, 98% hydro for Norway. Obviously, they live in the mountains. But the UK's got the Bristol Channel, you know. So, yeah, that's incredible. And then another incredible system is the Denort Reservoir. Now, this is a fantastic demo of what is done in the UK that is brilliant. It's an unsung, basically, this is an unsung success story. It was built to be stable, buffering power for nuclear power generation. But this system, which is a lake draining through some huge turbines, I think 6 of them. Let's just go to a picture of those. Here's the lake. Drains through 16 enormous turbines. There's one of them. 6 of them. And this can generate power, right, of 0 up to, I think, 1.5 gigawatts or 2 gigawatts in 20 seconds. When you turn the tap on, you get 2 gigawatts for about an hour or 2 hours. And that system creates the stability that's required for the UK national grid. And others as well. Scotland's got quite a lot of hydro that buffers the demand, smooths out the demand requirements for the UK. And these hydro turbines are working at the absolute best efficiency. The in and out efficiency of this system, I think, is 80%, 75 or 80%, because the turbines are working at 90% plus efficiency. It's so beautiful. I mean, this has been going for 30 plus years. It's incredible. So there are these success stories, but they just don't really look very trendy, and they haven't got dresses on, or, you know, they haven't got bling on. So they get overlooked and perhaps thought to be not great answers, but in fact they are. And of course it uses water. Beautiful stuff.
So we've got a question from GH, who says, who are the small British companies spearheading this? We need to support them or set one up.
Certainly we do, yes. We got some energy from something called low CO2, actually, which was using hydro from some of the rivers, including the River Wharfe up in Yorkshire, which we were with. But sadly, that company got absorbed, I think, by a solar PV company, which was really annoying. And so I don't know what happened with their hydro. But there are, good energy. Does anyone know Good Energy will look for micro power generators, which includes local micro hydro. So.
Yes, the capacity for sort of some form of community energy, isn't there? But
yes.
Yeah, really, really exciting projects. Thank you, Will. Any more questions before we start to wind up? We just had a comment, by the way, from just going back to the Tidal, the Lagoon Tidal, from Charles, who said he thinks the project leader was a dodgy geezer. Perhaps that's things somewhat.
Okay, right, okay. Yeah. I mean, you know, and that makes it difficult when, but from the actual physics and engineering and stability point of view, it's a no-brainer.
Yeah, and points to Carew Tidal Mill in Pembrokeshire, restored example of a medieval tidal lagoon, well worth visiting.
Right, okay, yeah.
Right, excellent. Unless anyone's got any more questions or comments, just want to say really huge thank you, Will, for your expertise and your enthusiasm, starting us off with the Archimedes, taking us to your kitchen, and then taking us to the wider world and the massive potential there is for hydro. So it raises so many issues, doesn't it, about energy resilience and the energy mix, of course. So
yeah, it's all good fun.
Yeah,
and the kettle was steaming under the electricity meter, so don't do that at home.
Thank you for that safety warning, very useful. So yeah, thank you everyone for coming. really, it's good to have so many people and interesting questions as well. We're here usually every month. We haven't got a date for next month yet, but we're thinking of screening a film. So if you signed up for our events, you'll hear about that. Or on Eventbrite, likewise. You might know that it's Great Big Green Week across the country at the moment. That's run by the Climate Coalition. I know you're not all in Bedford, but I will just put that in the chat if you haven't seen it. Just find the chat now. It's disappeared.
I'll do a parting waving goodbye from Oscar. There he is.
Thank you, Oscar. And for the friend who lent you Oscar. So yes, there's a link in there in the chat about Great Big Green Week. There are
Oscar's
lots of
green as well.
things happening. Good.
Yeah.
There are events happening around the county as well. So if you know any, do share them on your various networks as well. We're hearing about the Bedford ones just because several of us are in Bedford. But it's an opportunity to sort of share good news stories, but also challenge where we can on what we want more of and what we want less of. Quite a few of the activities are about personal behaviour change. So it's all a mixture of lobbying and raising awareness and personal behaviour change as well. I think it's quite a good balance. Great Big Green Week. So I think that's it really. Thank you everyone again. I'm just going to also put, before we go, our YouTube link, because the recording of this and our other talks will be on there. If anyone wants to see what we've been doing in the past, not all of our talks, but most of them from the last few years are on there. So that's in the chat. So there's
Lucy, would it be
things.
possible for us to save the chat on this occasion and maybe make it available? Because there are some interesting links and ideas, I think.
Yeah, we could put it on the website.
And Willard's got any that he wants to add in, any links as well. That would
Yeah, we've got lots of useful things, haven't we, on those? I think.
I also think maybe we can perhaps it'd be perhaps good to have a good review page for the council's site as well, because they've got some nice information there, and there's certainly more information has come through, I think, in the last few years.
Yeah, I mean, I think that this presentation of yours has been really positive, just to be really positive about something locally. There were lots of naysayers about the original. I'm not talking about Anne, who was suggesting, better alternatives. I know Anne is really well informed and cares. But I think some people were just slamming the scheme without any sort of alternatives. And I think it's good to see that it is on track to pay back, and it's generating what was predicted, perhaps a little bit more. And
I think it can be improved.
As you said, with some tweaks, it could be doing even more, which it's really good to be talking to council officers about. So thank you for that. So thanks, everyone. See you soon. And thanks again, Will and Colin, for helping out. Really appreciate you as always. And have a nice evening, everyone.
Great. Thanks, Lucy. Thanks, BCCF.